Oh, hello. In this topic, Lecture 6 is a statistical learning theory. We will literally deal with a statistical learning theory, mainly distance between true data, to estimate the distance between true data and estimated data. If a true data is Qx is given by sampling, we get the sample data. Based on this data, we can estimate value. To estimate the difference between true data and estimated data, there are two ways to distance between true data and estimated data. As you see, Kullback divergence and P. Wasserstein, and that is my not main topic, and another total variation, and so on. Our main topic is Kullback divergence and Wasserstein metric. As I said, that is to estimate the gap between true data and estimate data. And obviously, if the value gap is small, that estimated is very good sampling, as very good estimation. Otherwise, if the value, such a value is big, then it is not good data. Anyway, that is the motivation to we should know how the two concepts of the two concepts to estimate between two data. But in order to know this concept, it is essential to understand what is a measure theory or what is a probability theory. The two concepts, including a total variation, even if I will not deal with in this lecture. Anyway, that to understand these guys a measure or probability theory essentially. Okay, briefly in this lecture is not main topic to teach the measure theory and probability theory. If you understand this theory, see another textbook. In this lecture, I will very briefly summarize what is the concept of the measure theory, what is the probability theory, to understand between two concepts, Kullback divergence and Wasserstein metric. Okay. And the first step is to understand what is a measure space. We call the X is set a given. We can define sigma algebra. Okay, empty set and whole set is contained in M, and closed to complement and closed to countable union. Or in some sense that is similar to axiom of topological space, but a little different. In topology, in case of topology, finite intersection is closed, whereas in measure theory, in case of sigma algebra, M is closed to complement, And if the subset of power set M satisfies this condition, we call M is a sigma algebra. Based on sigma algebra, we can construct a map from sigma algebra to extended real number value system. And if so-called this, we can choose a set, but the sigma algebra goes to a specific spew out a specific value. So some say that that function is called a set function. Anyway, set function satisfies these two conditions: empty set spew out 0, and the value is all non-negative for any sigma algebra. And if the set satisfies countable additivity, if two sets are disjoint, then union of a measure, a union of the set function is equal to like this. Then we call the set function mu is a measurable function. So if think about triplet, a set is given from a sigma algebra and a measure. The triplet is called a measure space. That definition is so abstract, but if we apply the probability, fundamental probability theory, we can understand the definition is maybe a little abstract. For example, consider a omega b p that is a probability. Consider a probability space. How we can construct a probability space? For example, x corresponding to x in this above is correspond to sample space. Okay, based on the sample space, we can consider a set, power set, because the guys is power set. That is it is better like this. That is a power set. Okay, consider all power set of the omega, empty, whole set omega, and h and t. What is h and t? I will toss a coin, and if you toss the coin in normal situation, that show our eye see a head or tail. Okay, so h correspond to this, t correspond to this. Okay, then b is a sigma algebra axiom. As you check, if not a head means a tail. If a coin is not a tail, that is a head. Okay, that is close to the complement. And if union h and t is equal to whole set omega, okay, that actually satisfies the sigma algebra axiom. So B is a sigma algebra. Okay. Then we can consider a function P, which is known as probability, that is domain set sigma algebra. In that case, consider, because the probability is fraction, so consider the domain is closed interval. In that case, what is 0 means? empty set is 0. That is, any event does not occur. And omega means that h and t, that is if it's estimated probability, if I toss a coin, the probability both tail head either tail or head, whenever we toss a coin, that our eye can see head and tail. So whole probability is 1. Explicitly, because it is impossible head and tail simultaneously occurs, that is disjoint. So by so-called, because it is independent, we can express the h head or tail is equal to the sum. That is, a half is 1. That is p omega. Okay. So when you compare to a sigma algebra, this is a general measure space, and consider a omega sample space and sigma algebra and probability. We can check that probability space is an example of a measure space. But note that, as you see, in fact, h and t is so abstract. What is mathematically h? What is mathematically t? We know h is a head and t is a tail. But that is our imagination. We can define the set. Set is a collection. What is h or what is t? It is not does not make sense. We consider what is a set of h, what collector of a set, what collector of a head, what collector of a tail. It does not make nonsense. So in this example, next example, I will deal with a measurable function, we can understand that concept as a random variable. Of course, I will write the concept of the random variable, but I will later in detail definition. My lecture note is okay. Example definition 6.3. I will deal with a measurable function. My lecture note, that is point definition 6.1. That is example 6.2. Okay. Then, here, what is a measurable function? Okay, we consider two measure space. If a measure does not define two pair is called a measurable space. So consider two measurable space, and consider a function from x and y. Then we call the function f is a measurable function if for any we can choose a sigma algebra, its inverse is also in sigma algebra, but in this case N inverse map is a measurable space in M. That is difference. So we can understand, based on the concept, we can understand what is H and tail. As I said, that is not well defined set, but if we consider, see the following image, correspond each case is a number. Empty and whole set is nice, well-defined set, okay? Empty set is empty set. We know every element does not exist. That is empty set. Whole set is okay. But H and T, we, in that case, correspond 0 and 1. H is number, my numbering H is 0, and tail is 1. Head is 0. Okay? Then we know, we can understand H, head, we can translate head is just 0. Tail is 1. Then that is a little abstract and does not make sense. As a set, 0 and if we intersection 0 and 1, which means that the event simultaneously occur head and tail. That does not exist, so that is empty. And union, both either head or tail. If union, that is x, omega or x. So if we change the each case change as a number that is well defined, not only well defined, but also clever when comparing to what is set H, what is set T. Instead of this topic, 0 and 1 is a set. Okay. In that case, we can consider the following map. So, if we consider two x and omega, in the case of mu, that is a measurable function. Okay, in that case, the probability measure is a B, and that is F. That is abstract set. Anyway, that is a measurable function because we can consider the inverse image. Inverse image is also satisfies a sigma algebra axiom. It is clear. Just to change HT as switch HT as a number. Okay, that is a measurable space, and we can define the probability H is by H is written as the inverse image of H, and that is probability at x0. In the case, the probability, each case of probability by numbering we can define the probability like this. In that process, the set X is a random variable. Okay. Furthermore, if we consider a function f, X is abstract space, but domain is a real number. In that case, the definition is measurable is equivalent to like this. I cannot everything of measure theory, but it is very important in this to define the later definition. What is an integral and a measure space? Okay. And the important we should notice that the important properties of measure space. If a measure space is given, monotonicity and countable monotonicity is satisfied. If this is covariant property and countable monotonicity is also. So and a functorial is covariant property. That sign does not change. Okay. The proof is, the sketch of proof is make the set as a disjoint. Because disjoint set satisfies by definition of measure. What is it? Okay, countable additivity satisfies. So based on countable additivity, we can reconstruct a set like a disjoint. That is a main idea to check to verify a property of measure space. Sorry, because of my technical problem, I cannot upload image. Image cannot be edited, and because of a technical problem, I cannot write on image my text. So everything I will handwriting definition throughout the definition 6.6. Okay, sorry. Okay, so we can define next concept is define outer measure. The basic concept of the measure, outer measure, is based on the power set is given, subset is given, based on our ultimated problem by a set. From a set, we can construct a measure space. So to do this, we can consider set function that satisfies non-empty set is 0, and mu star satisfies monotonicity. That means that And the last property is countable subadditivity. That is similar to a definition of a measure, but that is not a measure because that is just set, but not sigma algebra. As I said, a sigma algebra, to be a sigma algebra, the set is domain of the set function. It should be sigma algebra. But that map, because we can start it from any power subset, that is just set function, not sigma algebra. Okay, so we can construct the next aim is to construct a sigma algebra. Okay. In this case, say M. Okay. If construct a sigma algebra M, if we construct the sigma algebra, then if we restrict, because this guy satisfies basic properties of the measure, but that is not just this problem, because it is just not a sigma algebra. So by restricting by sigma algebra, that becomes a measure. To do this, as I said, everything explained in detail in this lecture. We can define to construct a sigma algebra. We can define a collection of E, okay, and mu star satisfies for whenever every x is common. If we define this very miraculously and strangely, that's if we collect the M, that satisfies. Anyway, we can say the set is, we call mu star measurable, and that satisfies sigma algebra axiom. Okay, even zero set, see by proposition 6.7, zero measure sets. Okay, so zero measure set is also in M. That is your exercise. So if we collect the M, if the set correct E, it satisfies basic sigma algebra axiom, closed in countable union, closed in closed in the closed set and closed in countable union, and zero set is also in zero set, and so on. And so by restricting by mu star measurable, we can construct measure. Ultimately, if a set X is given, we can finally construct a measure by restricting outer measure. M is by defining mu star measurable. M. Okay. So the measure space is called a measure induced by outer measure mu star. Okay. Let's see example 6.3. 8. If we define the following set satisfies a measure, outer measure. That is so abstract, but if we understand this part, that is a fundamental step to construct a Lebesgue measure. So, in that case, if X is R, but in case A is, in that case, A is a subset of okay, that is power set, or that then in that case X is so abstract set. Well, I don't know what is the set X, but that is very specific set, a real number. And if we define outer measure, like example 6.8, that means that correspond to the ranks. Okay, so if we restrict R and we can define a sigma, a mu star measurable set, and mu star M, then that is a Lebesgue measure space, and ultimately if we say mu, and we can, because this guy is a real number, we can consider a set function interval is written as defined as b minus a. You see, now the length of the interval.